In this video, we will talk about moments and center of mass. So the whole point of this is basically, let's say you have some sort of piece of metal or whatever you want. And the whole point is that you want to figure out where exactly or what point P on this thin plate will make it balance horizontally. So if I have this fulcrum, so if I have like this little thing, and here is this point P, if I were to balance this thing on this little fulcrum, everything should just be balanced, perfectly balanced, nothing should fall. Okay, and that's what we call center of mass. So we're gonna first start off with the one-dimensional case. So let's do the 1D case. So let's say you have like this little rod, and in this rod you have two different masses. So let's say you have mass 1 and you have mass 2. Okay, and you want to figure out at what point will this rod balance completely. Okay, now obviously it's not the middle, because if these two are different masses, then in that case it will not balance correctly. So what we're gonna do is that, let's say this is the distance d1 from the first mass to the center, or wherever that center of mass will be, and then we're gonna have d2 be the distance between mass 2 all the way to that particular center. Okay, so we're gonna call the center of mass x bar. Okay, so I'm gonna write it right here. X bar is the center of mass. On this x-axis. Okay, so if I were to imagine this to be an axis, this is what it is. Okay, so this is what I'm gonna say. So let's say mass 1 is at some point x1, okay? And mass 2 is at some point x2, okay? So let's just say that's what it is. Okay, then this is what we can say. Then distance 1, so let's say this one, if this was supposed to be an x-axis, m1 is at x1, m2 is at x2. Okay, so what we can say is the following thing, that d1, the distance d1, is equal to x bar minus x1. And that makes sense, right? Because if x bar, the center is right here, the difference between x bar to wherever mass 1 is, that's just going to be the first distance, d1. Okay, and the distance d2, which is the second one, is going to be equal to x2 minus x bar. Because if you see x2, which is the bigger one, minus x bar, that's just going to give us the second distance. Okay, so that's what we can say. All right, now in order for this to be completely balanced, we know that for it to be completely balanced, the mass 1 times the distance 1 should equal the mass 2 times the distance 2. Okay, now I know what distance 1 is. I have mass 1. Okay, the distance 1 is just equal to this above part, x bar minus x1 is equal to mass 2, and d2 is going to be x2 minus x bar. x2 minus x bar. Okay, so now let me distribute this out. I'm going to have mass 1 times x bar minus mass 1 times x1 is equal mass 2 times x2 minus m2 times x bar. Okay, now what I'm going to do is I'm going to put all the x bars together. So I'm going to add this mass 2 x bar to the other side. Okay, so I'm going to have, mass 1 x bar plus mass 2 x bar minus mass 1 x1 equals mass 2 x2. And now what I'm going to do, I'm going to add m1 x1 to the other side. So this goes away, and I have mass 1 x bar plus mass 2 x bar is equal to mass 2 x2 plus mass 1 x1. I can factor out this x bar mass 1 plus mass 2 is equal to mass 2 x2 plus mass 1 x1. And then when I divide it, I have x bar is equal to mass 2 x2 plus mass 1 x1 divided by mass 1 plus mass 2. So if you can think about it, you are basically finding a weighted average. Okay, so this is basically the formula of where the center of mass will be at. If I have some sort of masses and I have I have the location of the masses, then it doesn't really matter what D1 and D2 are. All I need to know is what my masses are and what location they are at, and then I just add it to the sum of the masses. So this whole thing is, let me go ahead and write it a little bit better. We're going to call it summation from I goes from 1 to n of mass 1 x1 mi xi divided by the sum of the masses. So I don't necessarily have to have one mass or two masses. I can have many different masses, and then I can just go ahead and try to figure out what the center of mass would be based on all of these different weights. Okay. Now, it has a fancy name, which is basically called the moment of the system about the origin. So you don't really need to know that, but you just need to be able to use this particular formula. So let's just go ahead and give you an example on how we use this. Okay. Say we want to find center of mass based on the given information. So you have this particular thing, and here we have, let's say this is the x-axis. Here we have at x equals 10, you have a mass of 6, and here at x equals 50, you have a mass of 7. Okay, and what you want to do is find the center of mass. So let me call this M2. So I'll give you a minute if you want to go ahead and just take a second to try this problem out, and then I'll just go ahead and just do it. In order to do this problem, basically what you want to be able to do is just take the weighted, basically you can think about the weighted average. So you're taking the masses and multiplying it by whatever the location are, and then dividing it by the sum of the masses. So what you're going to have is mass 2, which is going to be 7 times 50, plus mass 1, 6 times 10, and then we're going to divide it by the sum of the masses, 7 plus 6. Okay, so if you go to your calculator, you can do 7 times 50 plus 6 times 10, and then we're going to divide it by 7 plus 6, and what I end up getting is 410 over 13, which is approximately equal to 31.54, I guess. Okay, so this thing will be the center of mass of this particular system. So if you wanted to figure out where exactly the balancing point would be at, it would be around 31.54. Okay, so the one-dimensional case is really, really simple to do. Let's go to the two-dimensional case. So let's say now you wanted to do it in 2D, so two-dimensional. Okay, so in this case, what we have is now we're going to add an extra axis. We have the x and the y, and now let's say that in the x and the y axis we have a couple masses. So here we have mass 1, here we have mass 2, and here maybe we have mass 3. And these have different locations, so you have you have an x and a y component. So for this type, we have something called moments. So I'm going to call this the moment about the x-axis. Okay, so here's the first type of moment, and we're going to call it this way. So we're going to call it m sub x. M just means moment, x just means about the x-axis. This is all it's going to be. It's just the sum of the masses with the y's, whatever the y component is. So you kind of are basically thinking about what exactly is the moment about away from the x-axis. So in that case, if you're looking at the x-axis, well, if you think about here being the x and looking at all these masses, notice that I have a horizontal distance of this particular of these masses. So all the vertical distances represent the y. So then for it would make sense that there should be the y component there. So then the moment about the y-axis will be exactly the same thing, but it will just be m sub y is equal to the sum of the masses, okay, mi times xi. So if you think about it that way, away from the y-axis, you can see that from the y-axis to the masses, you are going in a horizontal way, so it makes sense for it to be the x values, okay? So those are what we call the moments, and once we figure out what the moments are, then our center of mass will be x bar and also y bar, so you'll have two components. And the way that you do that is just basically you take the moment in the y direction, and you divide it by the total m, the sum of the masses, and then y bar will just be mx divided by m. And here m is just sum of masses. Okay? Very tricky formula, especially because you have the m sub y and the m sub x, and they are complete opposites of each other. Okay, so let's just do one quick problem with the 2D case. Okay, so let's just do an example. So let's just say find the moments and center of mass of the system. Okay, so let's say you have mass 1 is 3 at negative 1, 1. Mass 2 is 4 at 2 comma negative 1, and mass 3 is 8 at 3 comma 2. Now these can be in kilograms or in grams or something, okay, but they are just somewhere in space at these particular points. Okay, so you don't necessarily have to draw them out. You can just go ahead and immediately calculate it. You don't need to plot them out. So the first thing that we want to figure out is find the moments. So let's first find the moment about the x-axis. I'm sorry, that's not about the x-axis. So let's find the moment about the x-axis, which is going to be m sub y. Wrong, m sub x. Okay, so m sub x, all we're going to do is just take the mass. Okay, so we're going to take the masses, and we're going to multiply it by the y components. Okay, so that's going to be the moment about the x-axis. Okay, so what you're going to do, you're going to take each mass. So here's the mass, and here's the y component. So it's going to be 3 times 1 plus 4 times the y component, negative 1, plus 8 times the y component, which is going to be 2. Okay, and that's going to give me 15. Okay. All right, and now what we're going to do, we're going to find the moment about the y-axis. Okay, and we're going to say that that's a summation of mi times the xi's. Now we're going to do the masses again, so let me make this in a different color. Maybe this purple. So now we're going to take the 3, and I'm going to multiply it by whatever the x is, which is going to be negative 1, plus the 4, multiply it by whatever the x value is, which in this case is 2, plus this 8, multiply it by the x value, which in this case is 3. Okay, and what this is going to give me is 29. Okay, so we found our moments. Now all we have to do is now find the center of mass. So we know that the center of mass has this formula. So center of mass, x bar, comma y bar, is going to be equal to the moment in the y direction over the sum of the masses divided by the moment in the x direction divided by the sum of the masses. Okay, so now we know what the first one is going to be 29 divided by the sum of the masses. Okay, in this case, the sum of the masses is going to be 3 plus 4 plus 8. Okay, and then the moment in the x direction, okay, that's going to be 15, which is what we calculated, divided by 3 plus 4 plus 8. Okay, and those numbers come from these. Okay, and now all we have to do is just add them together. So in this case, you're going to have 29 over 15, comma 15 over 15, which gives us 29 over 15, comma 1. Okay, and that's basically what you do. So what this means is that if I were to plot all of these masses on an XY plane, whatever these may be, and I wanted to figure out where exactly would all of them balance out, then it would be at 29 over 15, comma 1, wherever the heck that may be. Okay, maybe that right there. That would be X bar, comma Y bar. Okay, so that's basically what you do. I think for the 1D and the 2D cases, discrete cases, is very self-explanatory. The only thing that's very a little bit tricky is just these formulas. And on an exam, you will actually have these formulas. You wouldn't have to memorize them because you can see that even I get a little bit tricked. So what I would suggest is that think about it as like, for example, the moment about the y-axis. Okay, think about the x component. So if you think about the y-axis being this, then you have some sort of mass right there, then in that way, you're talking about the x direction, okay, as opposed to the y direction. So here's the y-axis, and you're looking at how far this point is from the y-axis, and you can see that that relates with the x component, okay? All right, so I'm going to start talking right now, and that's basically the first part of center of mass.